Stars are powered by a nuclear reaction at their core. Fusion is the source of a star's power, which keeps them hot and allows them to produce light. Fusion also keeps a star from collapsing. Since the atoms at the core of the sun are heated to incredible temperatures, their motion and collisions create a gas pressure that pushes material outward, counteracting the gravitational forces that pull material in. This balance of outward gas pressure and inward gravitational forces keep a star in hydrostatic equilibrium. Chemical reactions are just one of the ways that energy can be released as heat. For millennia, humans have harnessed the energy of chemical reactions with the power of the campfire. Fire is a reaction that breaks the chemical bonds in the materials like wood, releasing excess energy as light and heat. However, the sun requires much more powerful source of energy to continuously burn for its 10 billion year lifetime. If the sun were made of wood and burned by conventional combustion, it would only last a few thousand years. Nuclear reactions are about 1 million times more energetic than chemical reactions, so they're a much better source of energy for stars to use. In fact, researchers here on Earth are trying to replicate the conditions at the center of the sun so that humanity can enjoy the abundant energy of nuclear fusion. In order to understand the difference between chemical and nuclear reactions, we need to understand the structure of an atom, its nucleus, and some of the subatomic particles like protons and neutrons. All atoms consist of a small, dense nucleus and a cloud of electrons bound by electromagnetic forces. Within the nucleus itself, there are two major components, protons and neutrons. Both protons and neutrons are made up of quarks, protons in such a way that they end up with a positive charge, and neutrons, which are neutrally charged. Both protons and neutrons weigh about the same, but the neutron is slightly heavier. Since the proton has a positive charge and like charges repel, all protons within the nucleus will repel one another. So why don't nucleuses explode due to this repulsion? Gravity and electromagnetism are only two of the four forces that exist in nature. The strong nuclear force is the third and is responsible for tightly binding protons and neutrons together in the nucleus. The strong nuclear force only works over very short distances, too short for us to experience in everyday life. But it's so strong that it can overcome the electrostatic repulsion between protons within the nucleus. The fourth force of nature is called the weak nuclear force and allows protons and neutrons to transform into one another. These types of transformations are the evidence that we have that protons and neutrons aren't themselves fundamental particles. They're composed of even smaller particles called quarks and gluons. On the other hand, electrons are fundamental particles. Scientists don't think we can take electrons apart into any smaller pieces. With a mass that's 2,000 times smaller than that of a proton, electrons are the zippy particles that have a negative electric charge. Additionally, all particles in nature have an antiparticle, kind of like an evil counterpart. Antiparticles share the same mass as their normal particle partners, but they have the opposite charge. For example, the antiparticle version of an electron is called a positron. When electrons and positrons come close to each other, they're attracted together by their opposite charges, and they destroy each other in an explosion of pure energy. Finally, the tiniest particles involved in nuclear reactions are neutrinos, a name that means little neutral ones. Neutrinos have a very, very tiny mass, so small that it's difficult to measure. We call neutrinos weakly interacting particles, since they do not have an electric charge, nor do they feel the strong nuclear force. The only forces that affect neutrinos is gravity, like all particles, and the weak nuclear force. This makes them very hard to detect since they emit no light and can pass through many thousands of kilometers of a dense material like lead without colliding with any of the other particles. That's our particle physics recap. Now let's look at a practical example. The simplest atom is hydrogen. Most hydrogen atoms contain only one proton in the nucleus, with a single electron orbiting far from the atom's core. in the cartoon picture like this one, the orbitals are shown as circular, planetary-like orbits, but that is not at all a correct picture of the atom. On small scales, the behavior of atoms is governed by quantum physics, so a better picture of the hydrogen atom would be smeared out into probability clouds. A scale model of hydrogen wouldn't look like this either. The distance between the electron and the proton is about 100,000 times wider than the radius of the proton itself. If you wanted to make a scale model of hydrogen, the distance between the electron and the proton should be 100,000 times larger than the radius of the proton itself. This is often why you hear the claim that atoms are mostly empty space. For example, if this pebble were the size of a proton, the electron would have to be more than 1 kilometer away. The proton, neutron, and electron are elementary particles. The strong and weak nuclear forces govern their behavior at very high energies. But in regular everyday life, we interact with matter through the electromagnetic force, which governs chemistry. A typical chemical reaction, like hydrogen and oxygen reacting to form water, is a process that breaks and forms chemical bonds between atoms. These chemical bonds are a complicated function of how the electrons are shared between different types of atoms, different elements. For example, if two hydrogen atoms come together with an oxygen atom, they can form a molecule of water, H2O, by sharing electrons in covalent bonds. The production of water is an example of an exothermic reaction, which means that the reaction releases heat. Chemical reactions interact through the electromagnetic force. What kind of reactions are nuclear reactions then? Nuclear reactions only take place between the protons and neutrons within the nucleus of an atom. Since protons are positively charged, they repel one another, but are held together by the strong nuclear force between the protons and the neutrons. By adding or subtracting protons and neutrons, new atomic nuclei can be created, but this takes a tremendous amount of energy. In a nuclear reaction, protons and neutrons can also be converted into one another, and new atomic nuclei can be created. There are two types of nuclear reactions: fusion and fission reactions. For very large atoms, like uranium-238, the proton-to-proton repulsion is so strong that across the width of the nucleus, there's enough electrostatic force to overcome the strong nuclear binding energy. Uranium-238 nuclei split on a timescale of 4.4 billion years. And when they do, they produce a thorium atom through the emission of an alpha particle. Alpha particles are just naked helium nuclei with no electrons to cover them up. When large atoms split into smaller ones, we call the process nuclear fission. I remember that fission breaks nuclei apart using the phrase fish and chips, or fish and chips. When I eat fish and chips, I break them into smaller pieces. Current nuclear reactor technologies here on Earth use fission reactions to release energy. NASA is even investigating nuclear fission for future space engines. You can also combine nuclei together, the reverse of fission, in a process called nuclear fusion. The word fusion means the process of joining two or more things together to form a single entity. In a nuclear fusion reaction, two or more small nuclei are joined together to form a bigger nucleus. Just like jazz fusion is a musical combination of jazz, funk, rock, and blues, so too can protons and neutrons jazz fusion together to form a bigger nuclei. Both fusion and fission reactions can release energy, but it depends on the details of the reaction. In the Sun, fusion reactions combine 4 hydrogen nuclei together to produce 1 helium nucleus, plus some energy. This process produces most of the Sun's energy. The most important nuclear reaction taking place in the core of the Sun is the fusion of hydrogen into helium. This reaction releases nuclear energy, the energy which powers the Sun. Rather than a cartoon, let's approach hydrogen fusion with more scientific notation. The reaction takes place in a few steps. 4 hydrogen atoms produce 1 helium nucleus plus 2 positrons plus 2 neutrinos plus 1 gamma-ray photon. A positron is denoted as E+ and is the antimatter partner of the electron. A neutrino is denoted with the Greek letter nu. The Greek letter gamma is used to denote light. The hydrogen fusion reaction is sometimes called the pp chain, since it involves protons, in other words, P. We can add up the mass of the 4 original hydrogen nuclei and compare it with the mass of the helium nucleus that is produced. We find that the helium weighs less than the sum of the 4 original hydrogen atoms. Some mass is lost during the fusion reaction. The mass is not really lost. It's been transformed into thermal energy, as described by Einstein's famous equation E equals mc squared. In this equation, m is the mass lost in the fusion process, c is the speed of light, and E is the energy that's released by the reaction, which now heats up the sun's core. The term c squared is such a large number that even tiny masses can be consumed in reactions and amplified into huge energies. The difference in mass before and after a nuclear reaction takes place is called the mass defect. The larger the mass defect, the larger the amount of energy that will be released in the reaction. Another related quantity is the binding energy of a nucleus. Any nucleus is made up of n number of neutrons and z number of protons, where n and z depend on the specific element. The binding energy is defined by adding the mass of all the protons and all the neutrons and subtracting the mass of the nucleus, and then multiplying by c squared. This binding energy is the amount of energy that you can extract from a reaction if you bind all the protons and neutrons into a nucleus. Alternatively, if you want to rip apart the nucleus, the binding energy is the amount of energy that you'd have to apply. In order for the fusion of hydrogen into helium to take place, the positively charged protons have to come close to each other before they can fuse. But positive particles repel one another, and we need to give the protons some extra energy so they can get close enough so the strong nuclear force can glue them together. This requires that the conditions in the sun's core be very hot and dense. Only the inner 25% of the sun is hot and dense enough for nuclear fusion to take place. The center of the sun is about 15 million degrees Kelvin, and the outer parts of the sun are too cool for nuclear reactions to take place. Since hydrogen is slowly being transformed into helium in the core of a star, this means that the star is slowly using up its fuel. Eventually, the core will be depleted of hydrogen, and the end of the hydrogen fusion in the core of a star signals the end of the main sequence stage of that star's life. Nuclear fusion of helium into carbon also releases energy. So this and other nuclear reactions that build up higher mass elements can take place in stars. But the heaviest element that can be formed by the nuclear fusion process is iron. Iron is a special element. In any nucleus, there's an interplay between the strong nuclear force, which has a small distance range and glues protons and neutrons together, and the electrostatic force, which is long range that wants to keep protons apart. Since the strong force is only strong at small distances, there's a special element, iron, which has the most tightly bound nucleus. This graph shows the binding energy of the nucleus of different elements. Energy is released in reactions that transform light elements into heavier elements, corresponding to downwards on this graph. Nuclear fusion releases energy when elements with masses as large as iron are formed. Similarly, nuclear fission can release energy as high mass elements are split into smaller ones, until they're as small as iron. But we cannot gain energy from iron by either breaking it apart or smashing 2 iron nuclei together. As no energy can be gained, a star that has accumulated iron in the process of nuclear fusion has nothing left for the star to feed on. Iron can't be used as fuel, and the star must die. This is sometimes called the iron catastrophe, which leads to the death of a star.